Okay, so there certainly is a reason for us to consider basic solutions, okay? It is because that we want the definition of basic feasible solutions. So what's that? Well, it's one kind of basic solutions that is feasible, so which means it satisfies the non-negativity constraints. So we know we have two sets of constraints, right? We have one set of functional constraints, and in a standard form, they are all equalities. So by the definition of basic solutions, all basic solutions satisfies AX equals B. So that's one thing. And also, we know whenever one solution satisfies AX equals B, the XB may be obtained by AB inverse B. And we have no way to tell whether this is non-negative or non-positive. All are possible. So if that solution XB happens to satisfy X non-negative, then all the constraints will be satisfied. And then we call it a basic feasible solution. So the definition is here. A basic feasible solution to a standard form problem is a basic solution which all the basic variables are non-negative. So we know we have 6 basic solutions in this particular example. We may see that the middle 2 solutions, they have negative terms as one of their basic variables. So in that case, they are not basic feasible solutions. The first, second, fifth, and the sixth solutions, they are basic feasible solutions because all the values here are non-basic, non-negative. So when we want a basic feasible solution, there must be a reason. The reason is because they are just extreme points. Okay, so our theorem is here. For a standard form linear program, a solution is an extreme point solution of the feasible region, if and only if it is a basic feasible solution to the linear program. So what's this? We are talking about standard form linear programs. Okay? For a standard form linear program, pretty much we know how to list all the basic feasible solutions. Because according to AX equals B, we are able to list all the basic solutions. And then we check non-negativity. We are able to list all the basic feasible solutions. And it turns out that they are exactly the set of extreme points to your original feasible region. Okay? So if that's the case, then the implication is clear. All we need to do is to deal with basic feasible solutions. For a standard form linear program, if there is an optimal solution, there is an optimal basic feasible solution. So later, when we formally introduce the simplex method, we will only focus on basic feasible solutions. So an unfortunate thing is that we don't really have time and enough mathematical tool to prove theorem 1 to you, but intuition are easy to be obtained. Let's take a look at some graphs to give you that intuition. Of course, you know that intuitions are never rigorous, but at least they help us understand what we're talking about and to give us some insights. So our example is still this one. So we were talking about this particular example. There, our original formulation says that 2x1 plus x2 should be less than or equal to 6, and x1 plus 2x2, that should be less than or equal to 6. All right? So when we want to get a standard form, we plus x3 here, plus x4 here, and both constraints becomes equality. That allows us to do all those listing for basic feasible solutions. Because we have 4 variables and we have 2 constraints, so each basis should contain 2 variables as basic solutions, as basic variables. Okay? So once we fix the 2 variables, we're going to solve a 2x2 linear system and try to obtain the values. Sometimes they are all non-negative. Sometimes some of them are positive, so are negative. So after all the enumeration, we will be able to check whether they are basic feasible solutions or not. Or say it in another way, we are able to list all the basic feasible solutions. And in this case, we actually may distinguish two sets of variables. x1 and x2, they are original variables, okay? And x3 and x4, they are slake variables. So you may consider x1 and x2 are some kind of production quantities for tables, for chairs, whatever. And the 6 and the 6 are the amount of resources you have. Resource 1, maybe that's machine hour. Resource 2, that may be labor hours. And then x3 and x4, they are just the amount of resource that you are not used. Something like that. So your solution basically is dealing with original variables. Here, each point, for example, B, it tells you that 3, 0 is a solution. You want to make 3 units of product 1, no units of product 2, and so on and so on. So what do we mean by having a basic feasible solution and convert that back to your original problem? Of course, is to focus on the original variables, okay? So your basic feasible solution, 1, has 4 variables, and we only focus on the original one. So your first basic feasible solution says, please set x1 to be 2 and x2 to be 2. Your second basic feasible solution says that, okay, I want 3, 0, and so on and so on. So in total, we have 4 basic feasible solutions. And it happens that we also have 4 extreme points, right? 1, 2, 3, 4. We have 4 extreme points for the feasible region for the original problem. In the original problem, you only have x1 and x2. That's how your feasible region looks like this part. And we may see that the solution A, 2, 2 is here. Solution B, 3, 0 is here. Solution E, 0, 3 is here. And then solution F, 0, 0 is here. So it turns out that maybe you may have a list of basic solutions. You don't know what are them, but that's fine. Because as long as you have a list of basic feasible solutions to your standard form, somehow they would be having some one-to-one correspondence with your extreme points to your original problems. Okay? So if you want to solve your original problems, all you need to do is to focus on their extreme points, right? And that just means you need to get your standard form and focus on their basic feasible solutions. Then you're done.